Okay? Okay, you guys will have to interrupt and ask questions, okay? If you get lost, you gotta ask. Okay, so it's about counting independent sets algorithmically, or we're going to sample independent sets from some distribution, and it's the results are related to phase transitions. I'll tell you what phase transitions mean and the connections, and then our work is building on this result of Dror-White's that I'm going to tell you about. It's a beautiful result, algorithmic result. So I'll tell you about that, and then I'll tell you a little bit about how we improve on it. I should have said at the beginning, so this is, these guys, everybody's at Georgia Tech. Ricardo and Linji are PhD students, and Jin Wu is a postdoc, who's actually, I think, is coming here soon to give a talk later this month. Okay. So this is what we're going to mainly be interested in this integer lattice, the grid, or small or finite subsections of it. And this problem comes up in several different areas, but in statistical physics it comes up as a model of a gas. So the idea is that the particles of the gas sit on these vertices of the grid, and they have some size, some mass to them. So they're big enough that two neighboring sites can't both be occupied. So a valid configuration, therefore, is an independent set on this graph, because you can't occupy neighboring sites. Okay? Now there's a parameter which is this lambda positive parameter, which is the fugacity of the gas. I have no idea what that means, but it sounds impressive. Maybe if you understand physics, you know what it means. I don't know what it means. It's sort of like the density, as far as I can tell. Okay, so this lambda controls the density of the typical density of the independent set. So we give a weight to an independent set, which is lambda to the size of the set. Okay, so if lambda is big, then we're favoring maximum independent sets. If lambda is 1, then all independent sets have the same size, same weight. And if lambda is less than 1, then we're preferring smaller independent sets. Okay? Now so now I'm going to look at this set cal I, which is a set of all, I'm going to have an input graph. Okay? And then cal I is going to be the collection of independent sets of this graph. And I'm going to have independent sets weighted by this lambda, and I'm going to look at this, first off, this probability distribution, where an independent set, its probability is proportional to the weight. In order to make it a distribution, I've got to normalize it so that it sums up to 1, right? And so the normalizing factor is, well, you just look at the sum over all independent sets of the weight. Okay, and then it's a valid probability distribution. Okay? So this thing is called the Gibbs distribution in physics. And what we want to do is the model is defined by this Gibbs distribution. In order to study the model, we want to be able to sample from this distribution. And that's how we can, so the idea is that the equilibrium state of the system comes from the Gibbs distribution. Okay, so if you want to run simulations, you've got to be able to sample from the Gibbs distribution. But how do you do that? How do you sample from that Gibbs distribution? It's hard because, first off, this distribution is defined over this collection of all independent sets of the graph. If a graph has n vertices, the number of independent sets is going to be huge. It's going to be exponential in n, typically. So you want to be able to do it in time polynomial in the size of the graph, even though the number of independent sets is exponential. So how do you do that? That's what we're trying to do by efficient, okay? And this normalizing factor is a sum over all independent sets, so you can't compute that thing explicitly. You got to do something clever. So, that's the end of the talk. Thank you for coming. That wasn't, what should I do? Oh, it's just me? Okay. Okay, so what do we, okay, yeah, so as I said before, so when lambda is 1, this partition function is just the number of independent sets of the graph, okay? We're going to look at algorithms we're going to look at the complexity of sampling from this distribution or estimating this partition function. If you can do one problem, you can do the other, vice versa. If you can sample from this, you can estimate this. If you can estimate this, you can sample from this distribution, okay? So they're very closely related. We want to know when can you do it efficiently, when is it intractable, NP hard, okay? And we also want to look at phase transitions on the infinite graphs, okay? I'll tell you what that means, the phase transitions mean, okay? And it turns out that this complexity of these problems, the algorithmic complexity, is closely related to phase transitions on this thing, okay? I'll tell you, phase transitions correspond to correlations, infinite correlations that persist, okay? I'll tell you more precisely what they mean and how they come up. Okay, just to preview, to help us a little bit, some intuition for later in the talk. Just some simple example. I just have a graph, it's just a single vertex. Then the partition function is just, well, so I have two independent sets. Either I occupy that one vertex that has weight lambda, or I have the empty set, which has weight 1. Okay, now I have a tree of depth 1, just a star graph, okay? Then either I occupy the root if I occupy the root, I can't do anything else. So that has weight lambda. Or the root is unoccupied. And then I have these delta independent vertices. And so each one, I can just go back and look at this, and I get this recursion, okay? So on trees, so what I want to get across is that if you think about it for a second, on trees you get a recursion. You can write the partition function for a tree of height h in terms of trees of height h minus 1 and h minus 2. Okay, so if you start going to a tree of depth 2, then either I occupy the root. If I occupy the root, then all of its children can't be occupied, and then I got delta squared independent vertices. So I get that. Or the root is unoccupied, and then I got these trees, these delta trees of G1. So I get these recursion, okay? So on trees, on complete trees, or even on, on trees, you can get some nice recursions, and you can do some computations and solve things exactly, okay? So that's going to come into play later. Okay, now, if I just take the simple case when lambda is 1, then that partition function corresponded to computing the cardinality of this set, the number of independent sets of the graph. I wanted to, lambda equals 1 was this case of I want to compute the number of independent sets of a graph. Okay, and I'm going to parameterize this problem by the maximum degree. Okay, this is just a special case of the problem before. This is the lambda equals 1 case. For this one, okay, so what do I know? The number of independent sets is often exponential in the size of the graph. My goal is to get an algorithm which polynomial in the size of the graph, but this problem is sharp-p complete. That's the counting analog of NP complete. So it's even harder than NP completeness. And that holds even when I restrict to the class of graphs which have maximum degree 3. It's still sharp-p complete. So I can't hope to do it exactly. I can't hope to compute, for all graphs of max degree 3, I can't hope to compute the number of independent sets exactly in polynomial time. Okay? If the max degree is 2, it's easy. Right? You just got cycles, you can, okay. Oh, yeah, so that holds for delta, any delta at least 3. Yeah. So delta equals 3 presumably would be the easiest one, so that's why. So the challenge was kind of reducing the delta. And then, so recently, not recently, but, okay, so, yeah, it holds for any delta.
So the difference between two results is the green and reduced to 3? Or?
Say, oh, well, Valiant first showed that it was the independent sets problem was sharply complete. And then, I mean, he maybe, I don't know if he showed it for graphs with max degree delta for some specific delta originally. And then slowly, but people started looking at graphs where I restrict to the max degree to be. And then they started getting the max degree down and down. So, yeah. Okay, so we can't do it exactly. This means that we can't hope to compute the number of independent sets exactly. Can we approximate it in polynomial time? Okay, so that's what we changed the focus to. And then more generally, this corresponds to the case lambda equals 1. More generally, I want to have any lambda, and I want to then compute this partition function, this weighted sum over independent sets. Okay? What do we mean by approximating the partition function? Well, there's two notions. Either I'm going to have a randomized scheme or a deterministic scheme, okay? And then what do we have? So this fpass, fptass or fpass. So I given my input is a graph and this approximation parameter epsilon. And I want to compute an answer which is within a multiplicative 1 plus or minus epsilon of the right answer. And that my algorithm should work for any epsilon and any graph in the class that I'm considering, okay? And my running time should be polynomial in the size of the graph and polynomial in 1 over epsilon. If that's the case, then it's a fully polynomial scheme, okay? That's deterministic, or sometimes we might only be able to get a randomized scheme. There we have an additional confidence parameter, and then we still want to get it within this multiplicative 1 plus or minus epsilon, but we're only correct with 1 minus little delta. And the running time is polynomial in log of this confidence factor. So, I mean, you can think of the probability of being correct within as being at least 3/4 or anything bigger than a half, and then you can boost it to this. Okay. So those are the two schemes. And then this is what I alluded to earlier. If you can get a scheme, a randomized scheme, to approximate the partition function, then you can sample from that Gibbs distribution. And if you can sample from that Gibbs distribution, you can approximate this partition function. I'll give you a little hint about how that, it's not too difficult. I'll give you a hint about one of the directions, okay, and the idea later in the talk. The usual scheme for these problems is that we try to solve this sampling problem by doing a Markov chain Monte Carlo approach. Okay? And in that approach, what happens is you have a random walk. The Markov chain is just a random walk on the space of all independent sets. And you choose a random vertex. You're at some independent set. You choose a random vertex. You try and update the independent set at that vertex, and then you keep walking around on the independent sets. Okay? That's the usual scheme. One of the amazing things about this Dror-White's approach that I'm going to tell you about is that he solved this. Well, he actually got a deterministic scheme for this partition function. He didn't use this Markov chain Monte Carlo approach. So he improved upon the best known results for using Markov chain Monte Carlo approach. He had a completely different scheme which directly approximated this partition function. So it's just an amazing approach when you see it. So, and there's this amazing results known, okay? This is incredible once you come to appreciate it. So there's, on the tree, so what at the top there, this T delta is the complete tree, infinite tree of degree delta. Okay, it's an infinite tree. There's this notion of phase transition on it, which occurs at this critical lambda. Okay, it's a function of the degree. As a function of the degree, there's a critical lambda where some phase transition happens. I'll tell you what it means precisely. But intuitively, it means I take this infinite tree and I ask whether the boundary influences the root. Okay, for small lambda, the boundary doesn't influence the root in the limit as the size of the tree goes to infinity. When lambda is big, then the influence of the leaves persist in the worst case, and they influence the root. Okay? And the critical point for that, you can actually compute it, because it's a tree, it's not that hard to compute it. It happens here, because you can use these recursions, and you can compute it exactly. So it's known it happens here. Okay? I'll tell you more precisely what all that means. Okay? So there's this critical point. Dror-White showed that there's a deterministic algorithm which, for any graph, when the maximum degree is constant, for any lambda less than this critical point on the tree. So it's any graph, but the critical point is the critical point from the tree. So it's like the tree is the worst case. But for any graph, when you're below this critical point on the tree, there's an algorithm to approximate the partition function. And you can approximate it arbitrarily close. Now, as soon as you get a little bit... Oh, shit. Oh, I can't swear, otherwise... Okay. So, for all lambda below that point, there's an algorithm, a efficient algorithm, an amazing algorithm. As soon as you get a little bit above that lambda, so I'm a little bit above that lambda, I can't get too far above. I mean, there's some small function, but the main thing is, as soon as I'm above that critical point, it's NP hard. So on one side, there's a deterministic, fully polynomial approximation scheme. As soon as I get above that critical point, all hope is lost. I can't even, I mean, before I said it was sharply hard to compute it exactly. Here I'm saying it's NP hard to approximate it. So I can't even get a good approximation for it. So as soon as I'm above, I can't get a good approximation for it. And when I'm below, there is not only a randomized scheme, there's a deterministic scheme, okay? So this side is just brand new, just 1 year ago, okay? So just to say a little bit more about this. This uses a very clever reduction, and then it uses this some sophisticated results. Mosa, Weitz, Wormald, who analyzed this Glauber dynamics. What they showed is that on random bipartite graphs, they show certain properties about independent sets, and their results held for this lambda just a little bit above this critical point. And then Sly uses that result in his as one of the components. And that's why, because their result only held for this small range of lambda, his result also only held for that. So we have a recent paper where we could extend their result to all lambda above this point, but we can only do it for 3 and at least 6. 4 and 5. You get these nasty, you can use the result from 3 to get it for 6 by just a little gadget. But then you get some nasty polynomials here that you got to deal with, and then they get even nastier as the delta grows, and so anyway. Okay, so now what I want to do in this paper, so Dror-White's is for general graphs. And this kind of resolves the picture for general graphs. There's this critical point, which happens at the tree threshold. One side you can approximate it for any graph below that lambda, and above that lambda it's NP hard. Okay? But what happens if I restrict myself to the integer lattice? Because that's the one that we're most interested in from the phase transition, or if you were going to focus on one graph, this would be perhaps the most interesting one to do. Okay? So Dror-White says that his result holds up to the tree of degree 4, which is 27 over 16. Okay? If you plug it into that formula at the top. Okay? So we want to see if we restrict ourselves to this graph, can we improve Dror-White's approach to get better results for this graph. Okay? That's what we're going to do. First off, what I want to do now is I want to just tell you what this phase transition means. Okay? And then I can tell you some more. Okay. So I hinted at it a little bit. So what I'm going to do is I'm going to take I'm working with finite graphs. So I take just I take the integer lattice. I just take some box, L by L box around the origin. Okay, and I'm interested in this distribution where the independent set has weight. An independent set has weight lambda to the size of the set. And what I want to do is I want to fix the boundary to be, say I fix the odd vertices on the boundary to be occupied. And I then sample from that distribution, conditional on that, and I ask the probability the origin is occupied. Okay? Or I fix it to be the even boundary, and then I'm ask the probability the origin is occupied. Right? If lambda is big, the maximum independent set is all even vertices or all odd vertices. If lambda's, well, that's always the maximum independent set. But if lambda's big, I'm favoring the maximum independent sets, right? So if lambda's big, then if by forcing, oh, that should be in there. So by forcing, oh, I guess there's a lot of them missing. Oh, yeah. Okay, yeah, 2 of them. And by fixing the even ones to be occupied, I'm encouraging the root to be, or the origin to be occupied too when lambda is big. If lambda is small, it doesn't really matter what I do on the boundary. And then over here, when by fixing the odd to be occupied, I'm discouraging the root to be occupied when lambda is big, in some sense. I mean, the maximum independent set does not contain the origin when I fix that. So I want to look at these two, and then what I want to ask is, well, suppose I take the, so there, if there's a finite boxes, then there is some difference between the marginal here and the marginal here, okay? But I want to ask, if I take the limit, so, and then I look at the difference in the marginal at the root, at the origin, is there some, does that difference persist or it dies off? If lambda is big, you would think that the difference at the origin persists because you're preferring larger and the maximum independent set. If lambda is small, then that it's going to die off. You know, certainly if lambda is tiny, then you know the smaller independent sets have bigger weight. So this influence is going to die off. Okay, so the belief is that there's a critical point, and below that, the influence dies off, and above that point, the influence persists. Okay. You can ask this. This is on the grid. You can ask this on the tree. You know, you can do the same thing. Ask, I fix the boundary, even vertices on the boundary or odd vertices on the boundary. I take an even-sized tree is what it corresponds to, or an odd-sized tree, and I ask whether for even-sized trees, the marginal at their origin versus odd-sized trees, do they have the same marginal for the origin, for the root? Okay. This thing is also corresponds to. This is, of course, is known as uniqueness. This is known as non-uniqueness region. The reason those terms comes because I define these probability distributions on finite graphs. I can also ask about if I take the integer, the infinite lattice, and I want to define some probability distribution on the infinite lattice. So there's a way to do it, and then I want to ask, is there a unique one on the infinite lattice, or is there multiple ones? And it turns out, so when the influence dies off, there's a unique one, because you can obtain these infinite measures by taking limits of finite ones, and all the limits are going to go to the same distribution, or there's multiple ones. Okay, so. Okay, so that's the phase transition. On the tree, you can use these recurrences about the partition function to figure out the critical point exactly. It's at that point. Okay, you kind of look at these recurrences about the partition function, and you look at some, you try to find some fixed point of it, and you see that the fixed point happens here, and stuff like that. So we know it for the tree, the complete tree, infinite tree of degree delta, we know it. But now what we really want to know it for is this integer lattice, the grid. So what's known? Well, they know that it happens at this point for a long time, okay? This is some simulations. I don't know how they do it, but they somehow, even before they had efficient computers, they had some way to estimate it, okay? Out to many digits, okay? The best known result, I mean, there was some way of using percolation to prove that the critical point was at least this. Dror-Weitz's general approach shows that any graph of max degree 4, the critical point is at least that of the tree. So that proves that it's at least 1.68. On the other side, well, it was hard to say what was known. It was kind of using standard techniques. One could show that the critical point is at most like something like 100. There was some related result by Dana Randall which shows something which intuitively is related, but which suggests that it should be less than this 8.8. And then after we started asking about this, they got inspired to think about it, and they haven't written the paper yet, but they seem to think they can get down here. So then we got this gap between here and here. So we just improved the lower bound to this 2.3. So we're still a long ways from here, but reasonable step. Okay, so that's what I want to tell you about today. Okay, so what we end up showing is that when lambda is less than this point, that these influence dies off in the limit. Okay, so in that phase transition, you also get an algorithm to compute the partition function for any finite subgraph. And also, if you're interested in this Markov chain, you get an efficient, you show that the mixing time is small. Okay, so you get all this stuff when lambda is less than. Okay. And we get there by improving on Weitz's result to take advantage of the Z2. Okay, so anything before I dive in?
How does the number come?
Oh, how is it? Oh, it's just computation. I mean, like it's not. I mean, you could certainly get a little bit better, and it's not like this is some threshold or anything. So, yeah, you'll see more. Yeah. You could certainly get a little bit better, and but we're still a ways from the right answer. So, okay. How's Dror-Weitz's result? I want to just explain the idea of Dror-Weitz's and then how we improve upon it. Okay? So, this is his idea for an algorithm to estimate this weighted sum over independent sets. Okay? So I got a graph, input graph. This graph has maximum degree delta, and I have an input lambda. This lambda is less than this critical point. Okay? Now, what is he going to do? Just choose any vertex of the graph. Doesn't matter how. Okay, fix one. What I want to do is I want to compute the marginal probability that this vertex is occupied or unoccupied. If I can compute that, suppose somehow I can compute that marginal for whether that vertex should be occupied or unoccupied in that distribution over independent sets. Then, well, with the correct marginal probability, I'll occupy the V. If I occupy V, then I should remove V and its neighbors from the graph, and then recurse on this smaller graph and repeat this algorithm. If V is unoccupied, well, then I should just rip out V and just take this smaller graph and recurse and repeat. Okay? But how do I do this one? That's the hard part. Okay? So okay, what he does. So what he does is he takes any graph. You give me any graph and a vertex in that graph. He's going to build a tree, because trees are easier to deal with. He's going to build a tree where the marginal for that vertex in that graph is the margin, the vertex. He's going to build a tree where the root corresponds to that vertex in that graph. And the marginal for the root of the tree is going to be exactly the same as the marginal of that vertex in the graph. So for any graph, I can build a tree where the marginal of the root equals the marginal of the vertex in that graph. And then I reduce the problem of computing the marginal in this graph to the computing the marginal for the vertex, for the root of a tree. And then I'm on a tree, it's easy. And it's amazing. For any graph, I can build a tree where the marginal exactly equals. It's not even approximate, it's exactly equal. So what does he do? He takes, what he does is he takes the tree that he builds is the self-avoiding walk. You take the graph and you start looking at all the self-avoiding walks, and that builds a tree. And then you have to do something particular for the leaves. So you start walking. So a path in the tree corresponds to a path in a walk in the graph. And once you complete a cycle, you stop. And that's make a leaf. And then I'm going to occupy or unoccupy that leaf in a particular way. If I do it in the right way, then I'll get the property I want. Okay, I'll show you what. So here's here's a graph. This is my graph. Suppose I want to compute the marginal for A. So I got AG is one walk. I got A, I, J, B, and then from B I can either close the cycle or I can continue on. I can go down to E, and so I get all these different things. Whenever I complete a cycle, I stop. Okay? And then I'm going to do something. So that's the tree. Now these leaves, these corresponds to unoccupied, and these correspond to occupied. I'm going to occupy them or unoccupy them in the correct way. He chooses the correct way, and then he gets this property about the marginal probabilities. How does he occupy the leaves? Well, so first off, look at take this A, I, J, B, E, D. A, I, J, B, E, D. And then I stop when I got back to A. So the end of this path corresponds to A, I, J, B, D, B, E, D. Oh, so it's a cycle. Well, all these paths, right, they end at a cycle, right? That's by definition. So the leaf ends with some cycle. Say it's something like this. What do? So for each vertex, what I do at the beginning is I fix some ordering on the neighbors in the graph. So A has got some ordering on its neighbors. Just fix it any way you want. It's on the grid, so you can just define some ordering based on north, east, south, and west if you want. Okay? And then I take this cycle and I look at the first edge or the first neighbor versus the last neighbor. And I say whether, I look at C versus E in this ordering, and if it's bigger, I say unoccupied. If it's smaller, I say occupied. That's it. So just based on this fixed ordering, I got to decide occupied or unoccupied, and that's it. And then, amazing, isn't it? So any graph, any vertex in that graph, I can build this self-avoiding walk tree, and the marginal of the root in this tree equals the marginal of this vertex in this graph. Now note, the one thing is this graph is much bigger, right? This tree is much bigger. B is appearing many times in this. Yeah, so I made a much bigger tree and the marginal, so that's one thing, okay? Okay. So this is his thing. This is the marginal, the probability the vertex is unoccupied in this distribution over this graph equals the marginal for this vertex in this tree. This tree is the self-avoiding walk tree, constructed in that way, with that particular boundary condition, okay? That's what he showed. Now, okay. That's the first component of his algorithm. But the problem is that this tree is big. So I can't do some brute force. I need a little bit more clever ideas in order to efficiently compute the marginal of that root, because the tree is potentially much bigger than the graph itself. Okay, so I still got to use a little bit of cleverness to get the marginal for that root of the tree. Okay, because it's such a big tree. So this is what the second component. What he's going to show is that what I want to do is I want to say on this tree, I don't have to go too far down the tree. Suppose I show that I only have to go down something like log n depth in this tree. Okay? So I only have to go below log n depth. It doesn't matter what the tree looks like. Okay? So I'm going to show that on a tree that whatever happens on depth log n, below that has very little influence on the root. So I'm going to show some decay of correlations. Okay, so below depth log n has very little correlation with the root, influence on the root. Okay, if I can show that, then I can just ignore everything below depth log n, and then the size of this tree is delta to the log n. So that's like n to the delta. So if delta is constant, then I got polynomial time algorithm. Okay. So that's what I got to show. So I got to show some decay of correlations. So that's what this SSM, strong spatial mixing, is a type of, it's a decay of correlations. Okay, I'll tell you what that means precisely. Okay. Yeah, what does it mean on the tree? First off, before I tell you what strong mixing, spatial mixing, I got to tell you what weak spatial mixing is. Okay. So weak spatial mixing says I got this tree, 2 copies of the tree. This is the same tree. I put 2 different boundary conditions, okay? So I take some vertices and I fix those green vertices to be occupied or unoccupied. So these guys are unoccupied, these guys are occupied. And over here I fix them to be something different, okay? And I want to say, I want for this boundary condition, what's the marginal at the root? For this boundary condition, what's the marginal at the root? Weak mixing says the marginal at the root for the worst 2 for 2 configurations, for 2 boundary conditions, the marginal at the root, the difference, is going to decay exponentially. So gamma is something less than 1. So it's going to decay exponentially in the distance from the green to the root. Okay? So the distance from the boundary condition to the root, the influence is going to decay exponentially in that. Okay? So, but notice, there might be one green guy which is close to the root, which I fix to be occupied or unoccupied. But maybe I take a child of the root and I fix it to be occupied in both. And the only differences are down here. So I have the 2 boundary conditions, like this thing. This one is fixed to be unoccupied in both. So you think that would encourage the root to be the same. I mean, that would reduce this difference, because I fixed it to be the same thing in both. But my exponential decays with the distance to the green. So yeah, it takes too long. That's what it's. Oh yeah, maybe it tells me. So anyway, so weak mixing, it decays exponentially in the distance to the boundary. Okay, even if those vertices on the boundary are the same. In strong mixing, I instead look at the vertices which differ on the boundary, and I want my exponential to decay exponentially in the distance to the difference on the boundary. Okay, so if I have somebody who's fixed to be the same, that only helps me. That's what it's saying. Okay, so that's strong mixing. And then what do we, if we want to show, well anyway, so what Troy Weiss is going to show is he's going to show that this strong mixing holds on trees. And then that's going to allow them to give an algorithm to compute the marginal at the root of the trees. Okay? And then, yeah, so what does he show? He shows that for every tree of max degree delta, when lambda is less than the critical point on the complete tree, then you have strong spatial mixing on any tree. So whenever you're less than the critical point on the tree, on the complete tree, every other tree has strong spatial mixing. Therefore, the correlations decay. So when you want to compute the marginal on any tree, you only have to go log n depth. Okay? So what we do is we want to look at the trees that arise when you look at we want to take the self-avoiding walk trees. We're just interested in Z2, okay? So we're not going to get all trees. When we look at the self-avoiding walk trees for Z2, we get a particular type of tree in there, family of trees in there, okay? So we want to look at that family of trees, and we want to get something better. He's getting a result which holds for all trees of max degree delta. We want to take this family of trees, and we want to prove something better for this family of trees about when this correlations hold. So we want to show for lambda bigger than that we still have this strong spatial mixing on this family of trees that come about from Z2. Okay? So what do we want to do? How do you describe these trees that you get about from this? I mean, these. We want some way to describe this family of trees that come about from the self-avoiding walks of Z2. It's a nice, but they're not if it's a regular tree, then not regular in terms of the degree, but if it has a nice structure, then you can try to analyze the recurrences and you can prove stuff about it, okay? But these things are not, they don't have that nice structure. But what we can define, so we're going to define what are we going to do? We're going to have a matrix M, which is going to describe the family of trees that we can generate, okay? Now, so the family of trees generated by M, so M is a matrix with non-negative integer entries, okay? Now, if I have the root starts, it's a T by T matrix. The root starts as one of that corresponds to T different types, okay? The root corresponds to, say it's a type 1. So now I look at row 1, and then, so if the root, say, is of type 1, then I want to say that the number of children of type J is at most Mij. So that I look at row 1, and that tells me how many children of each type for type 1. Okay? And then I keep going based on this matrix. Okay? So if I take M as just this single entry, I get all trees of max degree. So if the matrix is just this simple thing, then I get all trees of degree of branching factor at most delta minus 1. I take this slightly more complicated one, and then I can have the root be of type 1, and then I got delta children of type 2, and then I can start to have branching factor. So then I get trees of degree delta, because the root can have branching delta, and then everybody else has got branching delta minus 1. Okay, so those are two simple examples. What we can do for Z2, well, I can get this simple matrix which captures the self-avoiding walks of Z2. What do? Instead, I'm going to define it. I'm going to look at the tree, the self-avoiding walks of Z2, and instead of stopping whenever I complete a cycle, I only stop when I complete a 4 cycle. Okay? If I complete an 8 cycle or a 16 cycle, I don't worry about it. I only stop when I complete a 4 cycle, okay? So this is going to be a super graph of the self-avoiding walk tree. Then, turns out that you can describe the family of trees that you create there by this simple matrix, okay? Because you can just start to, actually you look at the north, south, east, west, and you just got to encode, strings of length 4. So it turns out that there's a simple matrix. Actually, I can simulate it here. I have this corresponds to the, so I have this vertex as the root, and then I have its children are all of type 1. It corresponds to that. And then you get the 2 of the children are of type 2, and then 1 guy is of type 1, and so on. And so it turns out that you can have this simple structure and you can capture the self-avoiding walks of Z2. And then, well, so we got this simple one by talking about 4 cycles. You can talk about 6 cycles, and you get a bigger matrix. You can talk about 8 cycles, you get a bigger matrix. Things start to get messier and messier. And then, now we have this family of trees. So we have a matrix. This describes the family of trees. We want to show we want to analyze this decay of correlations on this family of trees. How do we do it? So that's what we want to do. So the way one might try to do it is, so what you want to do is you want to say, so what do I got here? So this P for a vertex is I have some boundary condition eta. I'm asking in the tree, so I take this big tree. I take that vertex I'm interested in. I look at that subtree rooted at that vertex. And I ask, conditional on that boundary condition, what's the chance that vertex is unoccupied in that smaller tree? Okay? What I want to show that if I look at the marginal at a vertex for 2 different boundary conditions, the difference is smaller than the marginal at any of its children. So I have its children, and I look at the worst child. I look at the difference in the marginals from this pair of boundary conditions. And I want to say that for the parent, V is the parent of Wi, so that the difference in the marginals decreases as I go up. It decreases by a factor gamma as I go up. So that's going to imply that when I get up to the top of the tree, it's going to be like gamma to the height of the tree. Okay? I get some contraction at every level. So that's what I hope to prove. Turns out this fails. It doesn't work. It fails in the sense that even if I just try to use that approach to reprove Dror-Weitz's result for general complete trees or trees of max degree delta, I can't reprove it in that way. Okay? So what do I try instead? Well, the next thing I try is, this thing was described by some nice recurrence about the partition functions I kind of hinted at before. You can also look at this 2-level recursion, and you might think you might get something better. Doesn't turn out to help. But the key thing is what we do is instead of looking at the marginal at the vertex compared to the marginals for the children, I can just look at some potential function of these marginals. Okay? So I look at some potential function, phi. I'm going to define some phi, some function of the marginal, and I'm going to show for this function of the marginal at the vertex, it contracts compared to its children. So I can choose potential function and show it contracts with respect to that potential function, I'm still all set. So what's the potential function? Well, it turns out that there is some potential function. If you choose, then you get, for trees of max degree delta, you can reprove Dror-Weitz's result that you get this decay of correlations when lambda is less than this. This gives us an idea about some potential function to use for, this is for simple, this gives for all trees of max degree delta. We have a more complicated M. We can try to use the same statistic for this more complicated M to get for this other family, and that's what we do. So we look at this. We have a more general M. We take this statistic, which has got some parameters S. We find some S somehow. We computationally, we try some S. We see how, we see whether it contracts with respect to the S, and then we keep, we look around computationally for the best S. So we computationally look for the best potential function, and then we try to prove contraction with respect to this potential function. And then that's where it starts to become messy. Because to prove contraction for this potential function, well, we have some way to do it, and we have some condition. We have some, we can define some nasty condition. You define some matrix, and we can show that if this condition holds, if there exists some C where this condition holds, then that implies that potential function contracts, and then that implies you get this decay of correlations and everything else happens. So, and we get everything we want. So, and then, so what do we do? So we can, if we avoid these 4 cycles, we can get up to 2.1, and then when we start to look at these bigger and bigger family matrices, then we get, better and better. So, but we have these parameters that we have to find. We have these S and C that we got to find, and we computationally find them. Once we find them computationally, then we can verify it analytically, but we got to search for them. So we can't really do it much beyond that. So that's it. Yeah, just some thoughts about why we're at here, we got up to here, we're still a long ways from the right answer, so it's not clear what we're missing. So just some thoughts about what we might be missing or not. That's it. Any questions?